Hello, everyone. My name is Song Guanghui. I'm from Xidian University, China. This is a joint work with Professor Cai Kui, Dr. Zhongxiong Wei, and Professor Li Yang. The title is a joint sneak pass and data detection for resistive random access memory. RAM is a promising candidate for the next generation of non-volatile memory technology, where it suffers a severe interference problem called snake pass. Um, Previous works mainly focused on suboptimal data detection schemes, which regarded the snake pass interference as noise. In this work, we propose a near optimal data detection scheme that can joint detect the data and snake pass. Let's first review the snake pass problem. Here is an example of a resistive memory array. Data bits 0 and 1 are stored in the memory cell by using high resistance state I0 and the low resistance state I1, respectively. A snake pass is an undesirable pass in the memory array during data reading. It originates from and returns to the selected cell for reading and traverses horizontally and vertically through low resistance cells. Therefore, it produces interference to the selected cell by reducing the reading resistance. A common way to solve the snake pass problem is introducing a selector in series to each memory cell. In this work, we consider 1D1R RAM, where the cell selector is a dial. If the cell selector work, all the snake paths could be eliminated, where cell selectors are also prone to errors due to the imperfection of memory fabrication and maintenance process, leading to the reoccurrence of a snake pass. For this model, the main challenge of data detection is cell correlation. Due to the data dependence of a snake pass, previous works proposed suboptimal data detection schemes by ignoring the cell correlation and treating snake pass interference as noise. In this work, we propose a joint data and snake pass detection, which utilize cell correlation. Therefore, near optimal performance can be achieved. Let's first look at our main idea behind the detection scheme. By observing that the readback signal of each cell is related to the cell selector failure locations, and the data in the SF rows and columns. We have the following data detection scheme. We first detect the select filler locations and the SF rows and columns based on the readback signal. We will show that as the array is large, this detection is very accurate. With the detected SF rows and columns, we can actually know the locations of a sneak path. Thus, we can further detect the remaining data with the ML detection. Therefore, the overall performance is near optimal. In this work, we assume each memory array has at most 2 select fillers. We first give some definitions. The cell with the high and low resistance states are called HRS and LRS cells, respectively. The cell with the snake path interference is called SP cell. We have the other definitions for SP support, SP supported row column, and SP row and column. And the critical cells and the SP row and column types are defined as follows. Here we provide a figure illustration for the above definitions. Now we are ready to give the detection scheme. We first show that by using probability theory, as the array is large, there is a one-to-one correspondence between SP support number and the SP row and the column type. So we first detect the SP row and column types of each row and columns. Based on the SP row and column types, we can determine the SP number of each row and column, and therefore the selector failure pattern of the array can be detected. Also based on this SP support vector, we can find the locations of the select failures for both single and double select failure case. In the double select failure case, we need to further detect the uncertain bits in the SF rows and columns. Based on the location of the select failures and the SF rows and columns, we can detect the snake path interference of the remaining cells. And the data of the remaining cell can be detected by using a double threshold detection. In the following, we give a BER lower bound for the optimal data detection and then provide some numerical results. The BER lower bound is derived under the assumption that the SF rows and columns are perfectly known. This figure illustrates the detection error rate of select failure locations versus the array size n. The detection error rate decreases rapidly with n, and the detection error rate, the detection is very accurate, even when the noise variance is very large. Interestingly, the detection BER of SF rows and columns approaches a constant value when n is large. With the detect the select failure location and the SF row and the columns, we have the detection BER, overall detection BER, as illustrated in the following two figures. It shows that our proposed data detection scheme outperforms the previous detection, and it actually approaches the BER lower bound of the optimal detection. Now let's conclude the talk. We proposed a joint snake path and a data detection scheme for RM. The scheme first detects the SF row, SF locations, and the SF rows and columns, based on which snake paths and the remaining data are detected. Further work, future works involve reducing the detection complexity and developing detection schemes for RM with more than 2 select failures. Thank you for your listening.